In today's lesson, we are going to learn about Newton's third law of motion. Here's kind of a weird way to think about Newton's third law of motion. It basically says that you can't touch something without it touching you back. And we'll get into more of the official saying in the next slide. Before we jump too much into Newton's third law, though, I do want to take a second to refresh on his first and second law. So Newton's first law states that an object in motion remains in motion, an object at rest stays at rest unless acted upon by an outside force. And that is when net force is equal to 0. His second law states that an object will accelerate in the direction of a net force. And so today we are going to learn about his third law. What Newton's third law now says is that for every action, there is an equal and opposite reaction. And I'm typing this on my iPad as I go, and so things aren't lining up perfect, but for every action there's an equal and opposite reaction. That is, there is an equal amount of force exerted on both objects, and they are acting in an opposite direction. For example, here when this man pulls on the spring, well, if he pulls, I don't know, I'm just going to make up a number, let's say he pulls with a 5 Newton force, the spring is actually pulling back with a 5 Newton force. Or there's this reaction as well, and this is a kind of weird one to students. If there's this action that the earth pulls on the ball, well, the reaction is the ball actually pulls on the earth, which is true. Every object that has mass has a gravitational pull. So even right now as you're sitting next to your partner, you are exerting a gravitational pull on one another. So another way to look at this is that forces always occur in pairs. That is, for any individual force, there is an equal and opposite action or reaction pair. So force pairs are always acting on two different objects. So force pairs are always acting on two objects exactly. Not one, not three. They're always acting on two different objects. So here's this action. If the action is that a bug hits the windshield, well, the reaction must be that the windshield hits the bug. And the reason for that is the action has two objects. It had the object of the bug and the object of the windshield. The reaction then is the windshield hits the bug. We have to be talking about those two objects and their reaction because any force has an action and reaction pair. If I were to give you the example with this Kleenex box here, balanced forces versus force pairs, well, let's look at the forces acting on this object. So Kleenex box is sitting on a table. If I say that this object has force of weight, well, it does. It has a force of weight acting down. So that, and then acting upward, the table exerts a normal force. So that is going to be a balanced force versus a force pair. So notice, I'm not talking about the action and the reaction in this case. I'm just talking about, oh, there's a normal force acting upward that is balanced out with a normal force acting downward. And we know it's a balanced force because the Kleenex box isn't moving. So these two forces are equal, and they are opposite in direction. So now we have talked about the balanced forces acting on this object. With that, each force has its own action-reaction pair. So if we look at the action of this Kleenex box and the reaction of it, well, since we're focusing on the normal force in this case, we need to focus on the action-reaction of the normal force. So we could say that the action is table pushes up on box. The reaction then, my iPad lets me, the reaction then is that the box pushes down on the table. So we now have a balanced force, which is these two forces, but this is a force pair. Or if we look at the force of weight in this case, again, we need to have an action and we need to have a reaction. So the action is a little bit easier to figure out, which is at the, well, it can be a little bit harder. What causes force of weight? Well, in this case, we can say the earth pulls on the box, because we need to focus on what action is causing this force of weight. So if our action then is earth pulls on the box, and that's what gives it force of weight, well, what's the reaction? We have to use these same two objects. So in this case, the reaction is the box pulls on the earth. And that can seem a little weird, but at the same time, any object that has mass exerts a gravitational pull, and we're focusing on specifically force of weight. So what two things are balancing each other out? Well, it's kind of this, and then table ties into it, but really the earth pulls on the box. Makes sense. The box does pull up on the earth. Now obviously the box has less mass, so it has less gravity, so its pull is much, much, much weaker than the earth, but that is the action-reaction pair. And Newton's third law is a perfect example of how a fish swims. For every action there is an equal and opposite reaction. So the way that a fish swims, and I'm going to draw my very elaborate goldfish here and give him a little smiley face, is that when he moves his tail, he is pushing the water backward. So then if that's the action, is that the fish pushes the water backward or pushes the water back. Then there is this reaction that is occurring in this direction, and that reaction would then have to be the water pushes on the fish. So again, any action-reaction, you have two objects. Here we have fish and water, water and fish. So those are the two actions. And so that's how a fish moves forward. Similar thing can be seen is if two students are standing on a skateboard. Well, if one student pushes off the other, both students move because they're exerting a force on one another. Fish moves in kind of the same way. If we look at this, which of the following forces is considered a force pair? Well, in this case, we have an action, bat pushes baseball to the right, the reaction, baseball pushes bat to the left. Or is it the other one? Action, bat pushes baseball to the right, reaction, air resistance pushes baseball to the left. Well, remembering that a force pair is going to be an action and a reaction, that means we can only have two objects. Bat, baseball, baseball, bat. Two objects, 1, 2, 1, 2. If we look at this one though, we now have bat and baseball, great. But here we suddenly bring in air resistance in baseball. So in that case, this is not going to be an action-reaction pair. This one, on the other hand, would be. Alright, so here we have a story. While driving down the road, an unfortunate bug strikes the windshield of a bus. Quite obviously, this is a case of Newton's third law of motion. The bug hit the windshield, and the windshield hit the bug. Which of these two forces is greater, the force on the bug or the force on the bus? And I would like you to discuss this with the person next to you. So now that you have had a chance to discuss with your partner which felt a greater force, I'm going to tell you, they both feel the same amount of force because Newton's third law says for every action there's an equal and opposite reaction. So they feel the same amount of force, and this is where students are like, that doesn't really make any sense. Well, let's kind of look at it. So using these different sized letters to kind of talk about it, if we think about both of them having an equal amount of force, and we know that net force of an object is equal to its mass times acceleration, well, the mass of the bug is absolutely tiny, and that's the smallest time I can draw right now. Let me see if I can draw a smaller M here. So the mass of the bug is tiny. Contrary to that, the mass of the bus is going to be huge. So now, in order for their forces to be equal, what must be true about their acceleration? Well, if one has a small mass, one has a large mass, something must change with their acceleration in order for this value to be equal. Well, yeah, it does. The bug is going to feel a ton of acceleration. The bus is hardly going to feel any. And that kind of makes sense when you think about it. The bug stops very, very quickly. It's going fast, bug is gone. Bus, on the other hand, does it slow down? Technically, a little bit. It technically feels a little acceleration. And if you think about, let's say instead there was 1 billion bugs suddenly hitting the windshield, is that going to slow the bus down? Well, yeah, it is, because each one is going to contribute a little bit to the bug, or to the bus slowing down. For those of you that like number values with stuff, let's say the bug had a mass of 0.002 kilograms, and let's say the bus had a mass of, I don't know, like 2,000 kilograms. Numbers probably aren't perfect, but I bet they're pretty close. Well, in order for them to feel the same amount of force, let's just say they both felt 2 newtons of force, we need to solve for the acceleration of each. So in this case, we want to rearrange our equation, so net force equals mass times acceleration. So therefore I want to solve for acceleration. I'm going to divide by mass, and therefore I have the equation that acceleration is equal to net force over an object's mass, which in this case we said our net force was 2 newtons, our mass was 0.002, and so we take our 2 newtons divided by 0.002 kilograms, and we find that the acceleration of this bug, and let me grab my calculator quick. So in this case, we find out that the bug would have an acceleration of 1,000 meters per second squared. Contrary to that, we would have the bus over here. And the bus is going to have acceleration, so we take our 2 newtons of force divided by 2,000 kilograms, and we find that the bus is going to feel an acceleration of 0.001 meters per second squared. Well, that kind of makes sense. The bug feels a ton of acceleration, bus hardly feels any. Alright, coming up on the last slides here. So a gun recoils when it is fired. The recoil is the result of an action-reaction force pair. As the gases from the gunpowder explosion expand, the gun pushes the bullet forward and the bullet pushes the gun backwards. The acceleration of the recoiling gun is greater than the acceleration of the bullet, smaller than the acceleration of the bullet, or the same size as the acceleration of the bullet. I would like you to now pause the video and please discuss this with the person next to you. And the correct answer, the acceleration of the recoiling gun is going to be smaller than the acceleration of the bullet. Similar to the bus and bug analogy, since the bullet has a smaller mass, it's going to feel much more acceleration. The gun has a larger mass, it's going to feel a smaller amount of acceleration.